All right, so let's talk about projections. Again, these are mathematical models which transform spherical coordinates to planar coordinates. And here's just a cartoon of what that looks like. You can think of a light bulb, and that's why we say projection, because we are projecting lines from the center of the sphere out to different shapes of planes. And we can fold and roll paper in a lot of different ways. Let's just kind of think about projections from a more artistic standpoint before we get into this mapping application. Here's a public artwork that involves projections. Viewed at a certain angle, it kind of looks like, I don't know, a tiger tunnel or something. But if we go in the right place, you can see it's actually a really cool piece of work here that uses the idea of projections, taking a three-dimensional system. So this is a three-dimensional walkway, right, with a roof, and using probably some math and some guessing and that kind of thing, they've been able to project this visually into a 2D plane. So your eyes see a 2D image that's projecting out of this 3D scene. So artists have done this for centuries. This is a Renaissance painting that has a funny projection. Can anyone see the hidden projected image in there, or distorted image? So if you bring a mirror to that and look in the right direction and kind of stretch it, I think if you view it from a certain angle or whatever, then you actually see a skull and some dark humor, or just, I don't know what's going on here, but they hit a skull in there. And what they've done is taken a three-dimensional type of situation and projected it through painting and mirrors and distortion onto that 2D surface. Here's another example of kind of a reverse projection, taking a cylindrical mirror. This person drew this chair so that all the light would collect on a cylinder and represent the flat image there. And this is called anamorphism. So we're kind of playing games back and forth between 2 dimensions and 3 dimensions here. There are a lot of strategies for projections. We've seen the cylindrical example. So taking a sheet of paper and just making a cylinder around the globe. We have conical projections, and we have what's called azimuthal, where we just project everything onto a flat plane. And each of these projections has their own strengths and weaknesses. They have different types of distortions. They represent the globe and parts of the globe differently and maybe more realistically, depending on what part of the globe we're looking at. So this conical projection will touch the globe, and maybe it'll touch it in 2 different places. These are called standard parallels. They're frequently used for mapping large areas or long areas that run east to west. So a conical projection might run, for example, Colorado has 3 strips. So Colorado's cut into thirds along these long strips. I'm pretty sure that's a conical projection that we'll look at. So here's the conical projection for the globe, called Albers conical projection. And then, of course, will be flattened out. It really distorts things. Obviously, where we are kind of in the middle is less distorted, and as you go out to the ends, you get a much more higher degree of distortion. Here's a cylindrical projection. This is good for long north-south areas. The UTM, the Universal Transverse Marketer System, is based off a cylindrical projection. And this cuts the globe into these slices that go up and down from the poles. We'll use UTM a lot. It's metric. And Colorado is mostly in one UTM zone, but towards the edge where we are, there's another one. Here's a map based on a cylindrical projection. You've seen this a lot. It shows Greenland as this massive thing, which like bigger than Africa, right? Same with Alaska. and Antarctica looks huge. So it really distorts the poles quite a bit. These are not as big as they appear. Finally, we have planar projections, and these are best used to represent the poles where we have circular regions that we're interested in. So if we want to have a map of the poles, we'll use a planar projection to show that. And so we get less distortion. You can see the kind of more accurate representation of Greenland here. Here's Africa again, more accurate representation of Alaska. So this is a good polar projection. Obviously, all of these come with distortions, and we can have distortions in shape, distance, direction, and area. We want projections that minimize distortion in certain things. And if we're interested in kind of representing things from a shape standpoint, then that's called a conformal projection that minimizes that. Projections that minimize distance errors are called equidistant. And then area are called equal area, and then direction are called true direction. So depending on what you want, what's most important to you, you might choose a different direction or projection for that, but you can't have them all at the same time, unfortunately. So now let's bring this back to coordinate systems. I'll stop it there.